Hello, my name is Brady Bolding and I'm a computer science major here at the University of Alabama and a member of the MUNIT Research Laboratory under the guidance of Dr. Aijun Song on his project for integrated communication and navigation for autonomous underwater vehicles. Despite humans inhabiting Earth for thousands of years, we have still only explored 27.3% of the ocean seaboard and only 0.001 to 0.006% of the deep ocean seaboard. To combat this, the MUNIT Research Laboratory is developing technologies through the use of autonomous underwater vehicles to better explore the ocean at large. One major issue with autonomous vehicles underwater is that they are not able to communicate with each other in typical ways that we'd see on land, such as GPS or other forms of communication that use radio waves, as water absorbs these electromagnetic waves. So instead, they turn to a form of acoustic signaling, such as sonar, that our lab has developed its own protocols for. We test these protocols in our simulator that we have made in the MUNIT laboratory. In this simulation, we combine 11 files total with various functions and that house both our vehicle functions that determine how our vehicle will run and how the sensors work, to our environment class that tells us how or designs the ocean environment around it, and all the way down to a file specifically for our communication. The communication style that I use in my simulation runs is a FDMA channel. So in the FDMA channel, each vehicle itself gets its own broadcast channel and then listens in on all of the other ones. One example of this would be Vehicle 1 would broadcast to Channel 1, and then it would then listen on channels 2 through 7 to another 7 vehicles, where it would then know where everyone else is at. The reason that I use the FDMA is just where each vehicle gets its own airtime to prevent communication overloss, because we only have 10 kilohertz of bandwidth, so each channel getting 1 kilohertz plus having 0.25 kilohertz as little wiggle room between the different channels to prevent overlap causing feedback issues leading to communication loss. When you combine all this, we only have room for about 7 channels in a 10 kilohertz bandwidth. One way in the future to add in more vehicles, there's a couple options. First off, we can modify the FDMA where up to 10 vehicles get into one FDMA channel to broadcast, and then they're giving a certain time where they can broadcast their messages. This would allow us to stack up multiple vehicles onto a single channel, leading to a more robust simulation with a lot more vehicles and a lot larger of an ocean. We can also turn off the communication method and allow each vehicle to see into each other's vehicle, which, while this isn't very practical for real life tests, this would be a good way to limit tests somewhat how the vehicles will perform if there is up to hopefully 100 vehicles in a swarm, and how they would work through a situation. The main reason our vehicles are communicating and what they are communicating is important factors for a particle swarm optimization algorithm. What is a particle swarm optimization algorithm, you might ask? It is an algorithm that, It is an algorithm that is decentralized, that the vehicles work through a problem determining off of concentrations they pick up along their way to determine the next best course of action and find the most efficient and quickest way to a source. So the main way they do that is by combining a bunch of different weights combined with velocity vectors and position vectors of both the personal vehicle's best location of concentration combined with the group's best location of concentration, and then combining it with its own current velocity, and it will slowly work its way through an ocean until it finds the source of pollution. One of the first main variable that I want to point out is the inertial weight coefficient, or W here. This coefficient essentially determines how tight or how broad of the turns the vehicles will take, while if it is a smaller weight coefficient such as 0.2 to 0.4, it'll take tighter, more narrow turns, as the current velocity has a lot less saying on the next velocity, while with a higher weight coefficient it will lead to more broad and more rounded turns, as the current velocity still has a major factor in its next heading. Another couple of variables that are important is the R1 and R2 values, which are randomized values on the fly that essentially prevent the vehicle from being stuck into one location for too long, as the numbers will eventually adjust to cause the vehicle to want to perform a different way. And then the last and arguably the most important coefficients for the particle swarm optimization algorithm is the C1 and C2 values. These two values in our simulation change throughout, and essentially what they decide is how heavy the G-best or the P-best values will be at a given point in time. So because we want the vehicles to explore early on in the simulation while working to find the solution more so at the end, basically take in all the knowledge they can at the start, use all that knowledge, and then quickly find the solution from there. We have it where the C1 value starts out as a higher value because the high minus the low will lead to, plus the low will lead to a higher value than the low minus the high, plus the high, which is how the C2 works. It's just inverse. And so essentially it leads to that more generalized search at the beginning and then a more concentrated search at the end. So far in my time at part of the lab, I have been working on the particle swarm optimization algorithm, trying to refine what the correct weights for the weight coefficient or the C1 and C2 values or the acceleration coefficients, and basically just determine what is the best course of variables, what is the correct weights, should we be less influential at the start on the personal best, basically start from the beginning to be more refined in your search, or should you have a lot broader of a time searching and then get refined as close to the end as humanly possible. Another thing that I have done on my time is to prevent the robots from cheating by using knowledge it's not supposed to have, and basically removing the factors that could allow them to cheat and exploit the simulation. The next steps I'm planning on taking is continuing to develop the PSO algorithm. I want to eventually add in 2 functions that will allow us to see how far the vehicles have traveled during a simulation and the time it took them to reach the source of pollution, to essentially get a better feel for how the vehicle is traveling and what all different parameters we need for if we do real person tests with these algorithms. So we'd be able to get a better feel for how much energy it would expend throughout a simulation due to how far and how long it went with its specific speeds. Another thing that I would like to do is update the non-communication model. This is kind of going back to the communication slide where instead of stacking the layers, we could just have each vehicle peer into the other for limit testing purposes, but currently it is not working on the current build of the simulation, so I would need to update that. Another major part that I am looking forward to doing is updating the PSO system from a particle swarm optimization algorithm onto an AI model. The specific one I am currently looking at using is a multi-agent proximal policy optimization AI model, which essentially allows you to use multiple agents to work together using a policy similar to a particle swarm optimization algorithm to slowly work through the ocean. And instead of relying on a single function, it would be an AI model working on it in the background. And then finally, a little side project for fun that I'm going to attempt to do on this project is take our simulation from current 2D software to 3D software using Unreal Engine 5. Thank you so much, and do I have any questions?
Yeah, I'm just curious, can you tell us what the transmission speed is in general, and can you also comment on like how the signal degradation goes, how far can the signal go, or how far can the vehicles be from each other?
So I do not know the exact speeds that it is transmitting off of the top of my head, but I do know that approximately 400 to 600 meters away in the simulation, the vehicles were not, I can go actually to this slide here. So we can kind of see at about 400 to 600 meters, the vehicles will begin, you'll see them begin to communicate and respond to one another, like the gray one there picked up late, and then you'll see here at about 400 to 600 meters, this teal color one will pick up on the communication and join the rest of the group. So the goal with having a lot more vehicles in a larger ocean would be to where that link of chain would be a lot more interconnected to one another so they could work together more efficiently. Next question.
So what are some advantages to the multi-agent proximal policy optimization AI model that you were talking about at the end there?
So one of the main advantages to the multi-agent proximal policy optimization model is that First off, with multi-agents, each vehicle can get its own agent so it can act independent of one another, so we can keep up the decentralized approach of the particle swarm optimization algorithm and basically not limit us to if a vehicle crashes or goes down during a real-life test, the vehicles would still be able to perform as normal. And then an advantage of the more proximal policy side of the AI model is that it is very good at handling changing speeds and velocities and updated metrics that are constantly being updated, as it is stable in those. And it also allows us to give a reward system for finding better concentration and even throw in a reward for exploring a large area of the ocean if we want that to be our main goal.
Could you go into a little more detail? You said something about like the vehicles cheating. Could you maybe go into a little more detail about what that means?
Yes, so when I said that the vehicles are cheating, it more so means that the vehicles are getting outside knowledge that they're not supposed to have. So for example, maybe they have the coordinates of the source at the start of the program or waypoints to access this source. So by removing that, then the vehicles are going off of their own knowledge.
Vehicle to do the simulation. How many vehicle are you testing up to now?
So the most I've done up to date is 20. Right now I'm mainly running on 7, trying to refine the PSO algorithm in and of itself before I move to update the communication methods and then go from there. But the main reason I'm wanting to do this, I know it's a little outside of the question, is to basically limit test ahead of time before technology catches up and allows us to do these kind of large vehicle tests in real life, as eventually bandwidth will be a lot less of a problem as we will find better ways to carry communication underwater, and the technology will continue to develop. So when we get to the day when 100 vehicle simulation is practical, I hope to be able to run a 100 vehicle test in real life.